So the last thing we're going to look at here with sine and cosine graphs is doing some different things with modeling data. So modeling basically consists of writing equations either based on a description for a sine or cosine graph or writing an equation based on what a graph looks like. So for this example here, we have to write an equation. We're going to do all these as sine graphs. Should make a note of that here. So we're going to write all these as sine graphs. We could also do it as cosine graphs, but since it doesn't specify, we're going to do all these as sine graphs. So here I'm going to write an equation for a sine graph that has an amplitude of 2, a period of pi, and a displacement of up 1. So amplitude of 2 means I'm going to basically start off my equation with a 2. Then I have my sine function. Then I'm going to put my b value in here. So if the period is pi, so remember that's not the b value, that's just what the period is. In order to find the b value, I have to use the formula for period, which is 2 pi over b. So I'm going to substitute this pi in for the period, and I'm going to solve this equation for b. And when I do that, I get a b value that equals 2. So the easiest thing to do here is to just put this over 1 and cross multiply. So that 2 is going to go here. So since there's no shifting involved, there's no parentheses for this, so I can put my x in here. And then the displacement's up 1, that's just plus 1 at the end. So that is my equation that I would have that fits this description for part A. For part B, I have, once again, a sine graph. We're just going to do this as a sine graph, or a sine function. So I have a period that's 3 pi over 2, a phase shift of pi over 4 to the right. So with this here, I have y equals, and since the amplitude for this has not changed from the original, I can just put my sine in here. Now I have to put my b value in. So once again, I'm going to take this period, this 3 pi over 2, and I'm going to set it equal to 2 pi over b. And I'm going to solve this equation for b. So the easiest way, once again, to do this is to cross multiply. And when I do that, I get a b value here that equals 4/3. So that's going to go here. Now with this, notice I do have a shift that's involved, so I need some parentheses here. So this is going to be x to the right is going to be minus pi over 4. So that's the equation there for part B. For part C, a couple different things happening here. So once again, we're still going to continue with this as a sine graph. So with this, I have a graph that's upside down, has an amplitude of 1/2, a period of 3 pi, and a phase shift of pi over 2 to the left. So I have a lot of different things going on with this. So I have y equals, and I'm going to start this with a negative since it's upside down. And if the amplitude is 1/2, that's going to come next. Then I have my sine function. Now the period. So I got to put my b value in here. So the period here is 3 pi. So I'm going to say 3 pi equals 2 pi over b. And when I solve that equation for b, I get a b value of 2/3. So that's going to go here. Then I have the shift. So I need some parentheses to show what the shift is. So this is going to be x. To the left is going to be plus, and then pi over 2 at the end. So that's the model for that right there. So that's just some different things for a written description. When we get into some different things with graphs, okay, what I want to do first when I take a look at these graphs here is, before I start writing equations, what I want to do is figure out what all these different values are: the amplitude, the period, the phase shift, the displacement. So remember that amplitude for this is defined by half the distance from the max to the min. Well, the maximum here is 2, the minimum here is -2, so the distance from here to here is 4, and half of 4 would be 2. So that's the amplitude here. The period, if you notice, the graph starts here and works its way all the way here from 0 to pi. So because of that, the period's pi. And when I go to do the b value for that, and I'm just going to kind of put this over here, I'd have pi equals 2 pi over b. And when I solve that for b, I get a b value that equals 2. So I'm going to need that when I go to write my equation. So with this here, if you notice, there doesn't really appear to be any sort of shift involved because I have what appears to be a sine graph here. And I know that the sine graph usually starts at 0, 0, which is where this graph starts here. So I don't appear to have any sort of phase shift that's involved. And then the displacement for this, one of the ways you can look at your graph and know if there's any sort of displacement is take a look at your maximum and minimum values. And if the y coordinates of those values are opposites, which in this case they are, this is positive 2, this is negative 2, that's telling me that there really isn't any displacement involved with this either. So now that I have those values, now I can write my equation here. So I have y equals, this will be 2 times the sine of 2x. And I'm getting this 2 here from that right there. So that's the equation that I have for part D there. For part E, I have what appears to be a cosine graph. And it appears to be a cosine graph because the graph starts up high, it makes a big loop down, and then it comes back up again. So, but once again, first thing I want to do here is I want to find what these values are. So I got amplitude, period, I got phase shift, and I have displacement. So the amplitude, so remember, that's going to be half the distance from the minimum to the maximum. So if you notice with this graph has a maximum at positive 1, it has a minimum at negative 1, and the distance from here to here is 2, and half of that would be positive 1. So that's the amplitude. The period for this, the graph appears to go from 0 all the way to pi to complete one full cycle. So the period here appears to be pi. So as far as the b value goes, and once again I'm just putting this off to the side, I got pi equals 2 pi over b. And when I solve that for b, I get a b value of 2. The phase shift, if you notice, remember that cosine usually starts at 0, 1, and this graph also starts right here at 0, 1. So there doesn't appear to be any phase shift that's involved with this, so I don't have that there. And then for the displacement, if you notice once again, your maximum and minimum values, those y coordinates appear to be opposites. So since that's true, this graph doesn't have any displacement also. So now when I write my equation, I have y equals, amplitude's 1, so I don't need to necessarily write 1, but I have cosine of, and here's my b value, cosine of 2x. And that's the equation for part E there. For part F, I got a couple different things happening here, but notice once again that this kind of looks like a sine graph. It sort of starts here, and it goes up, it goes down, and it comes back up again, back at 0. So I'm going to write this as if it were a sine graph, because that appears to be the general shape of this. So now when I do my values here, my amplitude, my period, my phase shift, and my displacement, so the amplitude here, if you notice, the graph goes up to -3 or up to +3, it goes down to -3, and the distance from -3 to 3 is 6. Half of that would be 3. So I got that there. The period for this graph goes from -pi/4 all the way to 15 pi/4. That distance from here to here is 4 pi. So mathematically speaking, you can find this 4 pi simply by taking the ending point. I'm just going to put this up top here. The ending point minus the starting point. And if you subtracted those two, that'll give you 4 pi. And that's something you can always do to find period. You can always take the ending point of the graph and subtract it from its starting point. So as far as the b value goes, just once again kind of putting that over here. So I have 4 pi equals 2 pi over b, and when I work that out, I get a b value of 1/2. So the phase shift, if you notice, the sine graph usually starts here at 0, 0. Well, this graph starts at -pi/4, so it appears this graph was shifted pi/4 to the left So I'm just going to make a note of that here to the left, pi over 4. And then the displacement, if you notice here, both your maximum and minimum values have y coordinates that are opposites. So that's kind of telling me here that there really isn't any displacement for this graph. So when I go to write the equation, this is going to be y equals 3 sine, here's my b value, 1/2. So I'm going to put that here. And then in parentheses, I'm going to have x plus pi over 4. So remember, I'm adding because the graph is shifting to the left. And that right there is the equation for part F. And then for part G, notice with this, I kind of have what appears to be an upside down cosine graph. So remember, the original cosine graph starts up high, it makes a big loop down, and then comes back up again. An upside down cosine graph starts down low, makes a big loop up, and then comes back down again. So I'm going to write this as if it were a cosine type of graph. So when I go to do my values here, my amplitude, my period, my shift, and the displacement, notice my maximum and minimum values. So here's my maximum value is 3, my minimum is -1. So the distance from -1 to 3 is 4, and half of 4 would be 2. So I got that there. The period for this, so I'm going to call this basically as my starting point. This is my ending point. So when I go from -pi/8 all the way to 3 pi/8, the distance there is going to be pi/2. So remember, mathematically speaking, you can always take where the graph ends minus where the graph starts. And if you do that, you would get pi/2. So the b value here, I got pi/2 equals 2 pi over b. So the b value, when I work this out, I get a b value that equals 4. So the phase shift, if you notice with this, that this point, even if it were upside down, would usually start here. But this graph was shifted to the left, pi/8. So I'm just going to make a note of that there. And then the displacement. If you notice now, you have maximum and minimum values that aren't opposites. I have a +3 and I have a -1. So if you take a look at your amplitude here, and you notice the amplitudes too, so what that basically means is my maximum value should be at +2. But if you notice with this maximum value actually goes up to +3, which basically means I had to take this graph, in order to get it up to 3, I had to take the graph and I had to shift it up 1. So now that I have these values in here, I can start to write the equation. So one thing to note of this, we originally mentioned that this graph was upside down, so I need to start this function with a negative. So I have -2, because that's the amplitude, cosine of 4. The shift here is to the left pi/8, so this will be x plus pi/8. And then finally the displacement up 1, so I have to add 1 at the end. And that's what the equation would be for this particular graph here. So that's part G. So whenever you have the graph of a function, make sure you identify first what type of shape the graph appears to be, then go through each of your different values, your amplitude, your period, your phase shifting, your displacement, and then once you do those things, then it makes it a little bit easier to write what the equation for the graph is. So the last thing we're going to finish up with modeling has some different things to do with your calculator. So the question here says, throughout the day, the depth of water at the end of a dock in Bar Harbor, Maine varies with the tides. The table shows the depths in feet at various times during the morning. So it gives you these times in the morning, from midnight all the way up to noon, and how deep the water would be at the harbor based on the given times. So this is a problem that you can use your calculator for and do what's called a sign regression. So before I get to the questions here, what I want to do is I want to take my calculator and I want to go to the L1 and L2 columns. So that's stat and then edit. And what I want to do is I want to put the times in L1. So I'm going to use midnight as being 0, and then each of the hours after midnight would be these values here. So 2 would be 2 a.m., 4 would be 4 a.m., all the way up to 12 noon being a 12. And here are all the depths at each of the given times that we have here. So before we get to the different questions, what I want to do is I want to take this and I'm going to do a trig function to model the data. So what I would like to do here is I'm going to go back to stat and I'm going to go to calculate. And this is part A, by the way, of this question here. So I'm going to go to stat, I'm going to go to calculate, and if you use your up arrow key and you look at down here where it says C, I have what's called a sign regression. So if I hit alpha and then the program key, I have sign regression. So I have my list. My x1 is my x list is an L1, my y list is an L2, and then I want to store this equation in for y1. So when I go to here where it says store regression equation, if I push alpha and then trace, I can put this equation in for y1 if I just push 1 here. So I'm going to do that, and then I'm going to calculate this. And when I calculate it, this is going to give me what the equation for this is going to be. So what I have here, and I'm just going to go to 2 places with this for each of these different parts. So I have an A value here, that's the amplitude of 5.72. I have a B value here of positive 0.48. I have a C value here of negative 0.40, and then a D value of 5.62. One of the things to note with this, and that is, notice in your calculator they put the B value inside the parentheses. So when you go to write this equation, when we do that, we want to make sure that we put our B value for this inside the parentheses, and it's the only time I would ever tell you to do this. So the equation for this is going to be y equals 5.72 sine of parentheses 0.48 x plus 0.4, that's a 4 there, plus 5.62. So that's just roughly what the trig function that models this data would be. So now for part B, it says find the depths at 9 a.m. and 3 p.m. So if I come back to my calculator here, and one of the reasons I wanted to store this equation in for y1 was because if I go to my table now, I can look up the answers to these 2 questions in a real quick and easy way. So remember, 9 a.m. would be 9 hours after midnight. So that would be an x value that equals 9. So we would say that the depth of the water at 9 a.m. we're approximating to be roughly 6.017 feet. The other part asks for what's the depth at 3 p.m. So remember, a 12 for x would represent noon, and 3 p.m. would represent a value for x that's 15. So I'd have a value here that's roughly 6.3053. So that's my value for, that's what the depth of the water would be at 3 p.m. And then finally, part C says a boat needs at least 10 feet of water to moor at the dock. During what times in the afternoon can it safely dock? So I'm going to come back to my table again here. And what I'm looking for is, when is the water at least 10 feet? So if I come through this here, what you're going to notice is, with each one of these, I'm not really getting a value here that comes up to be anywhere near 10 feet. So with this, let me check my tables again here. So if I come back to my table of values, I'm not really getting any values here that would have a depth of 10 feet. So because of that, I don't have any times that are in the afternoon per se where the boat could safely dock, because what I'm looking at here is 12 being noon, and any times that would be afternoon would be anything, any x values from 13 all the way up to say 24. And if I go up to 24 hours here, you'll notice that none of the depths end up being anything remotely close to 10 feet. So in this particular instance, what we would say here is that the boat cannot safely dock, because if it needs at least 10 feet of water, at least in the afternoon anyway, there isn't any times in the afternoon where the depth of the water is going to be at 10 feet. So that's part C. So that's just some different things that we do with sine and cosine graphs with modeling data. One of the things that we will look at next is going to be some of the different characteristics that are involved with the graph of the tangent function, as well as the graphs of the reciprocal functions, the graphs of the cosecant, the secant, and the cotangent as well.